So the topic of discussion today is the memory concordance, because we know that just to improve the performance, the distributed shared memory system uh, mostly rely on replicating the shared data items, and it also allows the concurrent accesses by many nodes. However, if the concurrent accesses are not carefully controlled, because it has to be very carefully controlled, if it is not controlled, then the memory access may be executed in the order which may be different from the expected one. So that is why it is necessary that the concurrent accesses must be carefully controlled. Now, a memory is said to be coherent if it is going to return the value for a particular read operation, and that value is always the value that is being expected by the client or the programmer. So if the programmer is expecting to have a read operation, and with the read operation it wants to return a value which is the most recently write value, then only the memory can be said to be the coherent. So just to maintain this coherence of the shared data item, we are in need of a mechanism that is going to control, that is going to synchronize the different accesses which is done by the different nodes, and it is very necessary to do that. Also, it is just for writing a correct program, a programmer needs to understand that how this concurrent updates to the shared memory has to be carried out. Now, the set of this allowable memory access ordering forms the memory consistency model. So as far as the consistency model is concerned, it is basically, it refers to the degree of the consistency that is required to be maintained for shared memory data, for the memory to work correctly for a certain set of the applications. We can define this as a set of the rules that application has to obey if it wants the distributed shared memory system to provide the degree of consistency which is going to guarantee by the consistency model. So the different models of the consistency have been proposed. We have a strict consistency model, sequential consistency model, causal consistency model, pipeline random access memory consistency model, processor consistency model, weak consistency model, as well as the release consistency model. And the word consistency is used to refer as a special kind of the coherence. So out of many consistency model, the first one is the strict consistency model. This strict consistency model is the strongest form of the memory coherence, which is having the most tough consistency requirement, most stringent consistency requirement. Now, a shared system, a shared memory system is set to support this strict consistency model if the value which is returned by a read operation on a memory address is always the same as the value which is being written by the most recent write operation to that particular address, irrespective of the location of the processes performing the read and the write operation. So meaning thereby all the writes instantaneously should be visible to all the processes. But as far as the implementation of the strict consistency model is concerned, it requires the existence of absolute global time so that the memory read or the memory write operation can be correctly ordered to make the meaning of most recent. However, the absolute synchronization of the clock of all the nodes in the distributed system is not possible. So if it is not possible, then the existence of the absolute global time in the distributed system is also not possible. Therefore, the implementation of this particular model, that is a strict consistency model, for the distributed shared memory system is practically not possible. Then the second one is the sequential consistency model. This sequential consistency model was proposed by Lamport, uh, in which, as we know, that if any shared memory system is going to support this sequential consistency model, if all the processes is going to see the same order of all the memory access operations on the shared memory. All the processes have to see the same order in which all the memory access operations are being done on the shared memory. Now, the exact order in which the memory access operations are mixed, it doesn't matter whether it is a read, write, write, whether it is read, read, write, whatever it may be. So if we take an example that if we have three operations, read operation R1, write operation W1, and read operation R2, and if all these three operations are performed on a memory address in the same order R1, W1, and R2, then any one of the ordering, then with R1, W1, R2, any one of the ordering such as R1, W1, R2, R1, R2, W1, W1, R1, R2, means there are 6 possibilities. So any one of these ordering of these 3 operations, reading, writing, and reading, is acceptable, but provided all the processes are going to see the same ordering. If any one of the process sees one of the ordering of the 3 operations and another process sees a different one, then the memory is not a sequential consistent memory. So every node, every process has to see the same ordering as far as the 3 operations are concerned. Now, the consistency requirement of this sequential consistency model seems to be weaker than that of the strict consistency model, because the sequential consistency model is not going to give the guarantee that a read operation on a particular memory address always return the same value as written by the most recent write operation to that particular address. It is not necessary. But even though if a distributed shared memory system supports the sequential consistency model, it has to implement by ensuring that no memory operation is going to start until all the previous one have been completed. That's why a sequential consistency model provides one copy semantics, because all the processes sharing a memory location always see exactly the same content stored in it. So that is why the most intuitively expected semantics for the memory coherence, this is the most important one. So therefore, sequential consistency model is acceptable by many of the applications. So the crunch of the sequential consistency model is that whatever way the operation is being performed on a particular memory address at a certain node, all the processes have to see the same sequence in which the operation is being performed. It may be R1, W1, R2, it may be W1, R1, R2, it may be R2, but every process has to see the same ordering. But if every process is seeing the same ordering as R1, W1, and R2, which is happening at a particular node on a particular memory address, that acceptable ordering will be an example of the strict consistent memory. But any ordering, all the processes which are associated should see whatever sequence it may be, every process has to see the same ordering. That is the meaning of the sequential consistency model. Now the causal consistency model. This this model is going to relax the requirement as far as the sequential consistency model is concerned, just to obtain the better concurrency. As in the sequential consistency model, besides that, in causal consistency model, all the processes have to see only those memory reference operations in the correct order, in the same order, that are potentially causally related. Meaning thereby the memory reference operations that are not potentially causally related may be seen by different processor in different orders. But those memory reference operations that are causally related must be seen by different processors in the same order. But if the operations are not causally related, then the different processors can see it in the different orders. So a memory reference operation is said to be potentially causally related. What is the meaning of that? Now, a memory reference operation is said to be potentially causally related to another memory reference operation if the first might have influenced in any way by the second one. Let us take an example that if a process performs a read operation followed by a write operation, then the write operation is potentially causally related to the read operation because computation of the value written may have depend in some way on the value which is obtained by the read operation. So in other words, you can say that the write operation performed by a process, if it is not causally related with the write operation which is performed by another process. So if the first process has not read either the value which is written by the second process that was directly or indirectly derived from the value written by the second process. If it is not so, then they are not causally related and they can see the different orders. So any shared memory system which is supporting this causal consistency model, if all the write operations that are potentially causally related are seen by all processes in the same correct order, or you can say it as a correct order. And write operations that are not potentially causally related may be seen by different processes by the in the different orders. Now, as far as this correct order is concerned, it means that if a write operation, suppose the write operation W2, and if it is causally related with another write operation W1, then the acceptable order will be W1 and then W2 because W2 is happening after W1. So W2 will be having certain effect due to W1 and W1 is causing W2, so they are causally related. So the acceptable order is W1 and W2. Why? Because the value which is written by W2 might have been influenced in some way by another value which is written by W1. So therefore, W1, W2 is the correct order, but W2, W1 is not the acceptable order. Now, the distributed shared memory system, which is supporting this causal consistency model, it is required to keep the track of each memory reference operation because it is dependent on which other memory reference operations are being performed. And this can be very easily done by constructing, by depicting, by maintaining a dependency graph for all memory access operations. So this is the third model which is known as causal consistency model. The fourth model is pipelined random access memory consistency model. This model is going to ensure that all the write operations performed by a single process are being seen by all other processes in the order in which they are being performed, as if all the write operations performed by a single process are in a pipeline. Meaning thereby, if a process P is going to perform any kind of write operation, all other processes will be seeing that a single process is doing certain write operation. By doing certain write operations and all the write operations are in a pipeline. So the write operations performed by the different processes may be seen by different processes in different orders. Now, if we take an example, suppose W11 and W12 are the two write operations which are being performed by process P1. In that order, means pehle W11 and then W12. And suppose W21 and W22 are the two write operations which is performed by a process P2. So we have two write operations which is performed by P1, that is W11, W12. And there are two write operations which is performed by by the process P2, that is W21 and W22. And the order is W11 is happening before W12 and W21 is happening before W22. So any other process, suppose a process P3 may see the order in which the process P1 and P2 is performing. It may be the order that is W11, W12 and W21 and W22. And another process P4 might be seeing the order in which P1 and P2 are performing. It may be W21, W22 and W11 and W12. So what happens in this consistency model, that is pipeline random access memory consistency model, that it can be implemented by simply sequencing the write operations by write operation which is being performed at each particular node independently of the write operation which is being performed on the other nodes. And this is going to give the better performance than the previous models which we have discussed, because a process need not to wait for a write operation to perform by it to complete before starting the next, because everything is in pipeline. It will first write one W1, then W2, then W3 and so on. It has not to wait that let first write operation has to complete and then it will go for the second write operation. So this pipeline random access memory consistency model is simple and it is also easy to implement, because as we have seen in sequential consistency, all the processes have to agree on the same order of the memory reference operations. But in this particular model, that is pipeline random access memory consistency model, all processes do not agree on the same order of the memory reference operation, but they start their operation, writing operation, in a sequence in a pipeline. So the next one is the processor consistency model. This processor consistency model was proposed after the pipeline random access memory consistency model. Seems to be similar to the last one, that is pipeline random access memory consistency model, but with an additional restriction which is being imposed as far as the memory coherence is concerned. So meaning thereby a processor consistency model is coherent, as well as it is going to add the pipeline random access memory consistency model also. Now, as far as the memory coherence is concerned, it means that that for any memory location, all the processes have to agree on the same order of all the write operations to that particular location. So what is the effect? The effect is the processor consistency ensures that all the write operations performed on the same memory location. How it doesn't matter that by which process it is being performed. It is not going to matter. So whatever write operation which is being performed on the same memory location are being seen by all the processors in the same order. And this requirement is in addition to the requirement which is imposed by the pipeline consistency model. So if we take the example of the same which we have discussed in pipeline consistency model, that if W1 and W2 are the write operation for writing for a writing process for the writing operation to the same memory location, suppose X, and all the processes must see them in the same order, that is W11 before W22 or W22 before W12. The meaning is very simple. It is going to mean that the processor consistency, both the processors, that is the rest of the processors as P3 and P4 must see the write operation in the same order. Either it will be W11, W12, W21, W22, or it may be W21, W22, and W11 and W12. So this is about the processor consistency model. And the second last is the weak consistency model. In this weak consistency model, the basic idea is to enforce the consistency on a group of memory reference operation instead of individual memory reference operation, as we have done in the previous model. It is designed to take the advantage of two characteristics which is very common in every kind of applications, many applications. The first is it is not necessary to show the changes in the memory done by every write operation to the other process. It is not necessary. And the result of the several write operations can be combined together and then send it to the other process whenever the other processes are in requirement of reading those write operations or those updated values of that particular block. If to understand this, I can go with an example. When suppose when a process is executing in its critical section, the other processes are not supposed to see the changes which is made by the process to the memory until the processor is going to exit from the critical section. So in this particular case, all the changes which are being made to the memory by the process while it is in the critical section need be made visible to the other processes only at a time when the processor is going to exit from the critical section. And the second point, the second characteristic is that the isolated accesses to the shared variable are rare. That is, in many applications, a process makes several accesses to a certain set of the shared variables and then have no access at all to the variables in this set for a long time. And on the basis of these two are going to frame a base for this weak consistency model. The first characteristic which is mentioned, that whenever a process is going to update, having a write operation, then it is not necessary that every write operation which a process is going to make, it is not necessary to highlight that writing operations to rest of the processes. And if the rest of the processes requires that, once it is finished, then only, and if they request for that, then only it should be highlighted, it should be visible to the rest. And second one is that isolated accesses means once the shared variables are accessed and it is being used by a certain process by using these shared variables, it may be possible that the next time it will not be accessing the same variables which has been accessed previously. So based on these two characteristic the weak consistency model has been designed. Now, whatever characteristic has been mentioned here, these characteristics imply the better performance, and the better performance can be achieved if the consistency is being enforcing a group of memory reference operation instead of the individual memory reference operation. So as far as the main problem in implementing the idea uh, to determine implementing this idea of weak consistency model based on these two characteristics uh, is to determine the idea is how to determine that the system, how the system will be able to know that at what time it has to show the changes which has been performed by a process to other processes, because every process has time associated with every process is different for the different applications, and there is no way for the system to know that at what time the process which has made changes has to be displayed. So therefore, the programmer is asked to tell to this to the system itself. So to just to um, uh, uh, just to it is asked to the programmer are asked to tell this to the system for their applications. So it is the responsibility of the programmer, and it is going to put an extra burden on the programmer too. Now, if any distributed shared memory system is going to support this weak consistency model, then it has to use a very special variable called the synchronization variable. And this synchronization variable is going to maintain the consistency. Now, as far as the operations on this are used to the purpose of this synchronization variable is to synchronize the memory. So how it works and how it happens. So a process is used to access the synchronization variable. And when a synchronization variable is being accessed by a process, the entire memory, entire shared memory is synchronized by making all the changes to the memory made by the processes and should be visible to all the other processes. Now, whenever we talk about memory synchronization in distributed shared memory, it is going to involve the propagating memory updates, which is done at a particular node to all other nodes, which is having a copy of the same memory address. So for supporting this weak consistency, uh, we have certain requirements, and that requirements must be met. The first requirement is that all the accesses to the synchronization variable, it must obey the sequential consistency semantics. All the previous write operation must be completed everywhere before an access to the synchronization variable is allowed, meaning thereby synchronization variable is not allowed to be accessed until unless all the previous write operations are going to complete everywhere. And the last one is that all the previous accesses to the synchronization variable must be completed before, because it may be possible that many one wants to access the synchronization variable. So it must be completed before the access which has to be given for the non-synchronization variable. So this weak consistency model provides the better performance, but as I told you, that it is going to give uh, extra burden and going to incur some cost, because it is going to be the extra burden as far as the programmers are concerned.